In this lesson, we're going to learn about the multivariate chain rule. The multivariate chain rule is kind of interesting in that obviously it's a skill that'll help you solve some questions, but as far as this course is concerned, you'll only use it once or twice following this particular lesson. So learn it, learn to use it, but it's not one that you need to stress about hugely. That said, there's a little bit of nuance, and there's also a pretty cool, nifty trick that comes through it in regards to implicit differentiation that we'll talk about towards the end. The chain rule. From single variable calculus, we learned that if y is a differentiable function of x, that is, y equals f of x, and x is a differentiable function of t, that is, x equals g of t, then the chain rule for functions of one variable states that dy dt equals dy dx times dx dt. And notice there's a funky formatting thing here. This should be variable states. And this is in Leibniz notation. Another way we learned this was if big f of x equals f of g of x, then big f prime of x equals f prime of g of x times g prime of x. We can extend this idea to functions in two variables. Again, a little typo to be learned with an extra e in there. The chain rule, case one. Suppose that z equals f of xy is a differentiable function of x and y, where x equals g of t and y equals h of t. Those are both differentiable functions of t. Then z is a differentiable function of t, and dz dt equals the partial of f with respect to x times dx dt, plus the partial of f with respect to y times dy dt. The proof of this is in the book, in case you're interested. Just so that you're seeing the language, we're saying that you have some z that's a function of x and y, and x is a function of t, y is a function of t. Notice that the z is a function of two variables, and so we have partial derivatives of x and y, but notice that x is a function of just one variable and y is a function of just one variable. So we have dx dt and dy dt, and all told, we have our z, even though it has intermediate variables, has only one independent variable t, and so again, we have the dz dt. And this is called a tree diagram. We'll talk about them a little bit more later, but I'm going to introduce them right from the get-go. Note that z equals f of g of t comma h of t, which means z can be expressed as a function of one variable t, hence the notation dz of t. Basically, what we're doing here is differentiating f with respect to each variable in it, and then multiplying each of these by the derivative of that variable with respect to t. The final step is to then add all this up, as you can see in the formula. Other ways to write the multivariate chain rule are dz dt equals the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt, or the partial of f with respect to t equals the partial of f with respect to x times dx dt plus partial of f with respect to y times dy dt, or the df dt, or derivative of f with respect to t, equals partial of f with respect to x times x prime of t plus partial of f with respect to y times dy dt. Example 1. Suppose that z equals x squared y, x equals t squared, and y equals t cubed. A. Use the chain rule to find dz dt. I'm going to begin by drawing the little picture and writing the formula. So we're saying that z is a function of x and y, which are in turn functions of t. And so we know that dz dt will equal the partial with respect to x, partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. And maybe we'll try doing this in color. So first we need to find dx dt. That will be 2xy. And then we need dx dt, which would be 2t. And then we need dz dy, which would be x squared. And then we need dy dt, which would be 3t squared. At this stage, notice we have x's, y's, and t's, and so we need to write everything just in terms of t. And so we will sub in. And so we're going to replace all of our x's with t squareds, and we'll replace our y with a t cubed. So this will be equal to 2 times t squared times y, which would be t cubed. Oops, t cubed, not y cubed, times the 2t plus x squared, which would be t squared squared times 3t squared. Altogether, this is 4t to the 6th plus 3t to the 6th, or 7t to the 6th. In part B, can we find dz dt an easier way? The answer is yes. We could take that original function, the z equals x squared, and then y, and we can do our substitution right from the outset. And so this would be equal to t squared squared from the get-go times t cubed, which is a funny way of writing that z equals t to the 7th. If z equals t to the 7th, then certainly dz dt equals 7t to the 6th. Same as we had the other way. You might say, why would we do it with method A instead of method B? It's that the method in B is not convenient as the number of variables increases. And so we need to know the more powerful technique for the more complicated questions. We'll also need it for a proof that comes in multivariable calculus. Example 2. Suppose you have a parametric curve C defined by x equals cosine of theta and y equals sine of theta, where theta represents time, and t equals x comma y, or t of x comma y equals the square root of xy plus y, and gives the temperature in the xy plane. Find the rate of change of temperature with respect to time as we move along C through xy equals 0, 1. So let's start with our little tree diagram. So we're saying that T, temperature, is a function of the location x and y, and the locations are functions of the angle theta. Okay, so that tells us that d big T, d theta, equals dt dx times dx d theta plus, oops, and some of these are partials, the partial of big T with respect to x times dy d theta, like that. And these are partials. Let me check to make sure I did partials above. Yes, I did. Good. All right, so the first, let's do this the same way, term by term. And notice we start with a partial derivative of t with respect to x. And so that will be, it looks like you can end up with a 2 root xy plus y in the denominator. And in the numerator, the partial with respect to x would just be a y. Here's the yellow part. And then dx d theta will be, that's the blue part. And it's going to be, looks like negative sine theta. That's a sine, not a 3. Plus a partial of t with respect to x, with respect to y. How interesting, another typo. That will be something divided by square root of xy plus y. Our numerator is going to be the partial derivative with respect to y, which would be x plus 1. So that's the green part. And then the partial derivative with respect of y with respect to theta would be cosine of theta. So let's see if we put, ooh, and there's another 2 missing. I've had a good amount of little things missing, but hopefully we've caught them all. So if we put all this stuff together, it looks like we have a common denominator, which is going to be 2 times the square root of sine theta cosine theta plus our y will be sine theta. And then our numerator is going to be y, which is sine theta, times negative sine theta, or negative sine squared theta, plus our x times cosine, which would be cosine squared theta, plus cosine theta. We could probably simplify this, but I'm not sure if we need to simplify it. So let's not worry about the simplification quite yet. Let's see if we can figure out what our theta is here. What is theta? So that point 0, 1 would be up here. So I'm going to guess, and we can verify that it looks like our theta equals pi over 2. Let's just double check that that worked. So if I put theta equals pi over 2 into cosine, I'm going to get 0. If I put theta equals pi over 2 into sine, I'm going to get 1. And so, yep, that does indeed work. So the question asks us to find the rate of change of temperature with respect to time as we move along C through the point 0, 1. And so what we need to do is we need to evaluate this function at theta equals pi over 2. So theta equals pi over 2. Sine would be 1. So this will be minus 1 plus 0 plus 0 divided by 2 times the square root of sine of pi over 2 is 1 times 0 plus 1. It's a very, very funny way of writing. Looks like negative 1 over 2. So here's our rate of change. At the point 0, 1. The same ideas hold in higher dimensional spaces. So for example, in example 3, suppose that w equals x cubed y squared z, where x equals t squared, y equals e to the t, and z equals the ln of t. Find dw dt. So here we have w as a function of x, y, and z, which are each functions of t. And so we're going to get that dw dt equals the partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt plus the partial of w with respect to z times dz dt. And if we went through and found these puppies, I don't think we have quite enough colors to do everything, but maybe we'll use just a couple colors here. So we want to find the partial of w with respect to x. That will be 3x squared y squared z. And then we want the dx dt, or derivative of x with respect to t. So that would be times 2t plus, now we could find the partial of w with respect to y. That would be 2x cubed yz times dy dt. dy dt is going to be e to the t, because the derivative of e to the t is e to the t, plus partial of w with respect to z. So plus, that looks like it's going to be x cubed y squared times dz dt, which would be 1 over t. So we found our derivative, but now it still has x, y, z's, and t's in it, and so we need to clean it up and get it into just one variable t. And so we have all the x's are going to be replaced by t squareds, and all of the y's will be replaced by e to the t's, and all of the z's will be replaced by ln of t's. Okay, so this will give us equals 3 times t squared and then our y is going to be e to the t squared times z, which is ln of t, times 2t, plus 2 times our x is t squared, times our y, which is e to the t, times our z, which is ln of t, times an e to the t from before, plus our x, which is t squared, but now cubed, times y squared, y, which is e to the t squared, times 1 over t. So if we clean all this stuff up, it looks like we have 6 t to the 5th e to the 2t ln of t plus 2 t squared e to the 2t ln of t plus, I got t to the 6th over t, so t to the 5th e to the 2t. I think we could clean that thing up if we wanted. pulling out the common factor of t squared e to the 2t, but I don't think we need to. Seems close, good enough for jazz. What if x and y are multivariable functions? The chain rule, case 2. Suppose that z equals f of xy is a differentiable function of x and y, where x equals g of st and y equals h of st. And these are both differentiable functions of s and t. Then the partial of z with respect to s is equal to the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s, and partial of z with respect to t equals partial of z with respect to x times the partial of x with respect to t plus the partial of z with respect to y times the partial of y with respect to t. Note that z equals f of g of s of t, comma, h of s of t is a function of s and t. Here we have two first-order partial derivatives. So if you think about this in terms of the tree diagram, notice that z is a function of the intermediate variables x and y, which are in turn functions of the dependent variable or independent variable s and t, independent variables s and t. And so the yellow is following this path, whereas the green is following the paths to the t's. Example 4. Find the first partial derivatives of z equals 2x sine 3y, where x equals st minus t squared, and y equals the square root of s squared plus t squared. So let's start by making our little diagram. So we know that z is a function of x and y, which are in turn functions of s and t, s and t. We want to find both partials. Let's start by finding the partial with respect to s. And so we know that the partial derivative of z with respect to s will be the partial of z with respect to x times the partial of x with respect to s, plus the partial of z with respect to y times the partial of y with respect to s. And let's see what this puppy is. So again, just using two colors, partial of z with respect to s would be, partial of z with respect to x will be 2e to the 2x times the partial of x with respect to s, which is just t, plus partial of z with respect to y will be 3e to the 2x cosine 3y times the partial of y with respect to s would be, looks like it's going to be s over the square root of s squared plus t squared. So it looks like if we substitute in for x and for y, looks like there's a common factor of e to the 2x. So this will be e to the 2 times x. X is s minus t squared. And then what's left behind is 2t plus 3 cosine of 3y. So that would be 3 root s squared plus t squared times s, all divided by square root of s squared plus t squared. Notice that term does not cancel because The one in the numerator is inside the cosine, the other one is in the denominator. So this is our yellow partial derivative of z with respect to s. Now let's see if we can find the pink partial derivative of z with respect to t. So here, partial derivative of z with respect to t will be partial derivative of z with respect to x. As the partial derivative of x with respect to t, plus the partial derivative of z with respect to y, as the partial derivative of y with respect to t. And all this stuff will be the pink partial derivative we're looking for. So notice that the blue parts are actually identical. So we're going to have a 2e to the 2x. But dx dt is going to be different. So that's going to be, what color do I want? Green. So dx dt will be s minus 2t plus dz dt is still going to be 3e to the 2x cosine 3y. And then we also need partial of y with respect to t. Partial of y with respect to t will be t over square root s squared plus t squared. Again, we can substitute in to see what these puppies are equal to. So remember the x is equal to st minus t squared. And we have a common factor of e to the t again. So we're going to have a e to the 2s minus t squared again, parenthesis 2 times s minus 2t plus 3 cosine of 3 root s squared plus t squared times t now over root s squared plus t squared. So there you have both of the first partial derivatives of z equal to e to the 2t sine 3y, where x and y are as given. Case 2 of the chain rule contains 3 types of variables. S and t are independent variables. So the ones down at the bottom of the tree. X and y are called intermediate variables. Those are the ones in the middle. And z is the dependent variable right at the top. To remember the chain rule, it's helpful to draw a tree diagram like we've been doing. We start at the top of the function itself and then branch out from that point. The first set of branches is for the intermediate variables in the function. From each of these endpoints, we put down a further set of branches that give deep independent variables. We connect each letter with a line, and each line represents a partial derivative as shown. Note that the letter in the numerator of the derivative is the upper node of the tree, and the letter in the denominator of the partial derivative is the lower node of the tree. Let me see if I can make that clear. So the letter in the numerator is the upper node. So here, for example, we've got a partial with respect to x, and the letter in the denominator of the partial derivative would go to below, right here. Or the partial with respect to z, and the partial of z with respect to y. So if you're trying to figure out which order to do it in, it actually makes kind of like height order, like you might imagine. To use this to get the chain rule, we start at the bottom, and for each branch that ends with the variable we want to take the derivative with respect to, s in this case, we move up the tree until we hit the top, multiplying the derivatives that we see along the set of branches. Once we've done this for each branch that ends at s, we then add the results up to get the chain rule for that given situation. Note that we don't usually put the derivatives in the tree. They're always an assumed part of the tree. Example 5, use a tree diagram to write down the chain rule for the given derivatives. So we want to find dw dt for w equals f of xyz, where x equals g of t, y equals h of t, and z equals p of t. So what we're saying is that you have w at the top, and it's a function of x, y, and z, and each of these are functions of t. So that tells us that our formula what we need is dw dt, and it's equal to the partial with respect to x, the partial of w with respect to x, times dx dt, plus the partial of w with respect to y. It's a scary looking y times dy dt, plus the partial of w with respect to z times dz dt. Just a reminder that you have partial derivatives first because w is a function of 3 variables, and then you have normal straight d's second because x, y, and z are just functions of 1 independent variable. The question just asked for a tree diagram. We've created the tree diagram. In part B, we want to find the formula to find the partial of w with respect to r for w equals f of xyz, where x equals g of str, y equals h of str, and z equals p of str. So here we're saying w is at the top. It's a function of x, y, and z, which are in turn functions of s, t, and r, s, t, and r, s, t, and r. And what we care about are the branches that end in r, which are these highlighted yellow ones. So the partial of w with respect to r will be the partial of w with respect to x times the partial of x with respect to r, plus the partial of w with respect to y times the partial of y with respect to r, plus the partial of w with respect to z times the partial of z with respect to r. So tree diagrams make it pretty easy to figure out what these formulas are. Here again, notice since every variable, both the dependent and the intermediate, is a function of more than one variable, notice we're always the curvy partial derivative d's throughout. So provided we write down the tree diagram, which is easy, the chain rule can be applied to most any situation we run across. The chain rule general case. Suppose that z equals f of x1, x2, xn, and is a differentiable function of the n variables x1, x2, xn, and that each xj is a differentiable function of m variables t1, t2, tm. Hence, I think this is a hence. Hence, dz dt, and these should be partials, the partial of z with respect to ti would be the partial of z with respect to x1 times the partial of x1 with respect to ti, plus the partial of z with respect to x2 times the partial of x2 with respect to ti, plus plus the partial of z with respect to xn times the partial of xn with respect to ti for each I 1, 2, all the way to m. And it's just a general case of what we've done before. Don't memorize it. Think about it. Just think about it as just a fancy way of writing out that tree diagram. We've now seen how to take first derivatives of these more complicated situations, but what about higher order derivatives? How do we do those? It's probably easiest to see how to deal with these with an example. So suppose Example 6. Compute the second partial of f with respect to theta for f of xy if x equals r cosine theta and y equals r of sine theta. And here, I think we're looking for a general function, so it's going to still have f's in our final answer because I didn't give you an equation for that f. Let's start with our tree diagram. Well, I should say first, we want to find the partial of f with respect to theta. And so we're starting with our f. It's a function of x and y, which are in turn functions of r and theta. And we want to follow the theta path because of the theta there. So we know that this is going to be equal to the partial of f with respect to x times the partial of x with respect to theta plus the partial of f with respect to y times the partial of y with respect to theta. So let's see. So partial of f with respect to x, we don't actually have a function given, so we'll just write this as fx. And then partial of x with respect to theta, that would be, looks like minus r sine theta. Plus partial of f with respect to y, that's fy. And then we have partial of y with respect to theta here. That will be, looks like r cosine theta. Something like that. Okay. And we might be able to simplify this just a little bit. So this would be like common factor of r. And then we have fy cosine theta minus fx sine theta. And please note that fx and fy are both functions of x and y. So next up, we want to find the second partial. So second, we want to find the second partial of f with respect to theta. And this is a little bit involved, just a heads up. But the first step is to recognize this is simply the partial with respect to theta of the partial of f with respect to theta, or the partial with respect to theta of the thing we found above, which is r fy cosine theta minus r fx sine theta. Here I've distributed the r throughout. And so this is itself isn't too bad. This itself isn't too bad. it will be the partial with respect to theta of Fy times, looks like we're going to have R times negative sine theta minus, looks like partial with respect to theta of Fx times, looks like I've got R cosine theta. Which is, let's see, what is that? That would be like a, this would be like saying minus R sine theta times the partial with respect to theta of partial of F with respect to Y minus R cosine theta times the partial with respect to theta of the partial of F with respect to X. So each of these two partial derivatives is going to take a little bit of doing. So if we have the partial derivative of F with respect to Y, that's a function of X and Y, and X and Y are in turn functions of R and theta. And so if we're trying to find the partial derivative of this thing with respect to theta, we are following down the theta paths of that. Okay. And similarly, so this is the, I should say this is the yellow one. Similarly, if we have the partial derivative with respect to F, or partial derivative of F with respect to X, that's a function of X and Y, which are in turn functions of R and theta, R and theta. This is the green bit right here. And we want the function, the partial derivative with respect to theta. So again, we're going to follow down the theta paths. So this is going to take a little bit of writing here to try to figure out what's going on. So all this stuff is going to be equal to minus R sine theta. And now we need that yellow formula, if you will. So that yellow formula is going to be partial derivative, second partial derivative of F, first with respect to Y, then with respect to X, times the partial derivative of X with respect to theta, plus the second partial of F, both with respect to Y, times the partial derivative of Y with respect to theta. So all of this is this yellow part, minus R cosine theta times the same thing. So now we're in the green part. So we're going to go second partial of F with respect to X times partial of X with respect to theta, plus second partial of F first with respect to X, then with respect to Y, times the partial of Y with respect to theta. And all this is the green stuff. All right. Well, this question is going to keep going, so let's go on to the next page. See if we can write this a little bit more cleanly. This will be equal to minus R sine theta times, this would be F of YX, and then we have maybe I'll write it as x sub theta plus f of y of theta. That's just the yellow part again. It's written more concisely. Minus r cosine theta f of x of theta plus f of x y theta. And that's the green part. Okay, what are these? Remember that x equals r cosine theta, y equals r sine theta. Pardon me. Minus r sine theta times f of yx. X theta would be r times negative sine theta plus fyy. This would be r cosine theta. Wait, so y equals r sine theta, so r cosine theta. So that's the yellow part. But now with the partials with respect to theta found, minus, oops, minus r cosine theta. Trying to find the green part. So that'll be fxx, x theta, r cosine. So this will be minus r cosine, r sine theta plus fxy. Y theta will be r cosine theta. This is the green part. Now let's see if we can find some common ground between our sines and our cosines. I'm hoping for something that will be good. I think there may be some hope here. So let's see. So there is an r squared in every term. So we can pull that out front. And so we have fx or fyx minus minus, so it'll be plus sine squared. Minus, we have fyy, sine cosine. And then we have plus fxx, sine cosine. And then we have minus fxy, cosine squared. Okay. Notice that you have the mixed partials, which, assuming everything is continuous, those are equal to each other. So since those are equal to each other, there's a common factor. This would be r squared times, we have a f of x y times, it looks like I've got like a sine squared theta minus cosine squared theta. And then if we focus on the mixed partials, we'll notice there's a sine cosine in common. So I have plus sine theta cosine theta times fxx minus fyy. I think this is going to give me some double angle formulas if I'm seeing what's going on right here. So I think this will be r squared times fxy, and then cosine squared minus sine squared would be cosine 2 theta. So I think this is going to be minus cosine 2 theta plus sine theta cosine theta times 2 would be sine of 2 theta. So this is 1/2 sine of 2 theta times fxx minus fyy. We go back to the beginning, make it a little bit bigger. So we first found our first partial, and we found our second partial. And there was definitely a lot of writing involved. But at the end of the day, we found a relatively nice formula for the second partial of f with respect to theta. History. The symbol used to denote partial derivatives is this curvy d. One of the first known uses of this symbol in mathematics is by the Marquis de Condorcet in 1770, who used it for partial differences. The modern partial derivative notation was created by André-Marie Legendre in 1786, although he later abandoned it. Carl Gustav Jacob Jacobi reintroduced the symbol in 1841. And so if it's not a symbol that you're really happy about, just remember that it took quite a few years for mathematicians to settle on it. How to draw it. It's sort of like the curvy 2s. No, that's a bad one. Like maybe you like do a 2 with a little swoop in it. It's sort of like that, but without the tail on it. So it's like a 2 that forgot its tail. Or you might think about it like a D that gets kind of a little bit hung over. Whatever works for you. Implicit differentiation. The final topic in this section is to revisit implicit differentiation. With these forms of the chain rule, implicit differentiation actually becomes a fairly simple process. Let's start out with a review of the implicit differentiation that we saw in a Calc 1 course. We will start with a function in the form big F of xy equals 0. If it's not in this form, simply move everything to one side of the equal sign to get it into this form, where y equals f of x. In single variable calculus, you were asked to find dy dx, and this was often a fairly messy process. Using the chain rule from this section, however, we can get a nice simple formula for doing this. We'll start by differentiating both sides of big F of xy equals 0 with respect to x. This will mean using the chain rule. So we're starting with big F, and we recognize that big F is a function of x and y. We know that x is a function just of x, and y is a function just of x. Notice there's kind of something funny with a whole bunch of x's floating in here. So our partial derivative, or our chain rule with respect to x, is going to require a partial derivative with respect of f with respect to x times the derivative of x with respect to x, that's here, and then plus the partial derivative of big F with respect to y times dy dx here. Note, really important, dx right here is just 1. So since that's just 1, we're going to have big F of big Fx, or partial derivative of big F with respect to x, plus the partial derivative of big F with respect to y times dy dx equals 0. Here we can solve for that dy dx by first subtracting the fx across and then dividing. So here's the minus big F of x divided by big F y. It could also be written as dy dx equals negative partial of f with respect to x divided by partial of f with respect to y. Example 7. Find dy dx for x cosine 3y plus x cubed y to the 5th equals 3x minus e to the xy. So if we want to use our formula, The first step is to move everything to one side. So this tells us that our big F of xy is equal to x cosine 3y plus x cubed y to the fifth minus 3x plus e to the xy. And this is all equal to 0. And then it tells us that dy dx is going to equal negative big Fx divided by big Fy, which would be partial derivative with respect to x, cosine of 3y plus 3x squared y to the fifth minus 3 plus y e to the xy. And there's a minus sign out front. And this is divided by the partial derivative of big F with respect to y, which would be negative 3x sine 3y plus 5x cubed y to the fourth plus 0 plus x e to the xy. Boom, implicit differentiation in 2 steps, much easier than before. If we have big F of xyz equals 0, with z equals f of xy, then we can find the partial of z with respect to x and the partial of z with respect to y using the chain rule. And so we're doing the same thing as before. So we're saying we start with our big F. It's a function of x, y, and z, and we know that x is a function of x, y is a function of y, and z is a function of x, y. So if we want to find the partial of z with respect to x, then want to find the partial of z with respect to x, then we're simply going to have partial of big F with respect to x times the partial of x with respect to x. Remember, that's going to be 1, plus the partial derivative of f with respect to y times dy dx, or partial derivative of y with respect to x. But notice that y isn't a function of x, so that's going to be 0, plus the partial derivative of f with respect to z times the partial of z with respect to x. That's this last branch. Right here, you've got partial of x with respect to x is 0, partial of y with respect to x is 0. You solve, at the end of the day, you're going to get the partial of z with respect to y equals negative partial of f with respect to y over partial of f with respect to z, and similarly partial of z with respect to, I guess I should be careful with my colors here. The partial of z with respect to x equals minus the partial of f with respect to x over the partial of f with respect to z. And if we went down the y path, then we would end up with the partial of z with respect to y equals minus the partial of f with respect to y divided by the partial of f with respect to z. Last example, example 8. Find the partial of z with respect to x and the partial of z with respect to y for x squared times sine of 2y minus 5z equal to 1 plus y times cosine of 6zx. So the first thing we're going to do is we're going to move all of this to one side. And so this means that we have some big F of x, y, z equal to x squared sine of 2y minus 5z minus 1 minus y cosine of 6zx equals 0. And so if we want to find the partial of the partial of z with respect to x, we're going to have minus big F of x divided by big F of z. Not of, I should say, big Fx divided by big Fz, not y, z. Also, or negative the partial derivative of f with respect to x divided by the partial derivative of f with respect to z, which would be negative partial derivative with respect to x, 2x sine of a whole bunch of garbage, minus 0, and then it looks like I'm going to have a minus 6yz. Derivative of cosine is negative sine, so it'll be a plus sine 6zx divided by partial derivative of f with respect to z. Here I'm going to need the chain rule. So I'm going to have a minus 5x squared. Derivative of sine is cosine. Cosine of 2y minus 5z minus 0 plus derivative with respect to z would be 6xy sine of 6zx. It's pretty crazy. It's like one step to do implicit differentiation, which I really like. So we could do the other one. So we wanted the partial derivative of z with respect to y. This will be negative big Fy over big Fz, or partial derivative of f with respect to y divided by partial derivative of f with respect to z. And this, the denominator is going to be the same in both cases, but the partial derivative with respect to y will be, looks like 2x squared cosine of 2y minus 5z minus 0 minus 1 times all that garbage cosine of 6zx divided by the same stuff as above, minus 5x squared cosine 2y minus 5z plus 6xy sine 6zx. And so there you have your implicit differentiation using partial derivatives. Much easier, much faster than what we did back in Calc 1. The formula isn't even that difficult to remember, right? It's this kind of these nice formulas like this. It's just that we don't use it often enough to remember it. So it's if you were doing a whole bunch of implicit differentiation, then it's probably a formula worth memorizing. If you're getting ready for an assessment, for a quiz, for a test, maybe it's worth remembering, but it's not one that's going to get used often enough that you'll probably have it at the tip of your tongue. So there is everything that you need to know about the multivariate chain rule. Thanks very much, and I'll see you on the next lesson.